Hello everyone, myself Rupalakshmi K, student of CSE Department at Sri Venkateswara College of Engineering. In this video, I'll be talking on a research paper in the field of cloud computing for the subject cloud computing. These are the contents discussed in the video. Research paper introduction. The title of the paper which I'll be discussing is Advancing Cloud Security, Unveiling the Productive Potential of Homophobic Secret Sharing in Secure Cloud Computing. As listed, there are five authors of the paper, and the paper was published in September 2020. Introduction. Cloud computing delivers services like servers, storage, and software over the internet, offering businesses flexibility, scalability, and access to resources without significant upfront investment. It plays a crucial role in enabling remote work and collaboration. However, the growing reliance on cloud services raises concern over data security, privacy, and compliance with regulations like GDPR and HIPAA as cyber attacks and data breaches increase. This paper focuses on enhancing cloud security through innovative techniques like homomorphic encryption and undercover sharing, aiming to create a secure and reliable computational platform. Objectives: investigate integration of homophobic encryption and undercover sharing, explore how combining homophobic encryption and undercover sharing techniques can work together to enhance cloud data security, enhance data security in cloud computing, assess how integrating these methods can provide stronger protection of sensitive information in cloud environments, develop a reliable and confidential computational platform, design a platform that ensures data privacy and security while supporting efficient computation process, distribute data across multiple servers, focuses on distributing data across its multiple servers to reduce the risks associated with single point of failure. Cloud computing security challenges. Cloud computing faces several security challenges, with data breaches being a major concern. Unauthorized access to sensitive information stored in the cloud can lead to data theft or loss, as seen in high profile incidents that have highlighted the vulnerabilities in cloud security. Another critical issue is unauthorized access, often stemming from weak authentication mechanisms, allowing malicious actors or insiders to misuse their privileges to exploit cloud resources. In addition, data loss remains a risk, whether due to accidental deletion, hardware failure, or malicious attacks, underscoring the need for robust backup and recovery solutions. Furthermore, insecure APIs pose significant risk, as attackers can exploit weakness in applications programming interfaces to gain unauthorized access or manipulate data. These challenges highlighted the importance of protecting sensitive information such as personal or financial records. Ensuring the data security in cloud is crucial not only to comply with regulations like GDPR but also to avoid reputational damage and financial losses for organizations. Homomorphic encryption. Homomorphic encryption is an advanced encryption technique that allows computations to be performed directly on encrypted data without the need to decrypt it first. This innovative method enables secure data processing while keeping the original information confidential, providing a powerful solution for protecting sensitive data in cloud environments. The significance of homomorphic encryption lies in the ability to perform operations on data without exposing it to the potential threats, making it ideal for scenarios where privacy is important. This process works by allowing users to send encrypted data to the cloud, where computations are carried out on the encrypted information. The cloud then returns an encrypted result, which the user can decrypt to get the final output. This ensures the originality of the data remains secure throughout the entire process. The key benefit of this technique is the data is confidential during the processing, significantly reducing the risk of breaches or unauthorized access while allowing efficient, secure computations in the cloud. Undercover sharing techniques. Undercover sharing techniques offer a robust method of protecting sensitive information by dividing the data into multiple parts and distributing them across different servers or locations. This ensures that no single server has complete access to the full dataset, greatly enhancing security and privacy. The process begins with data segmentation, where sensitive data is split into smaller encrypted segments. Each segment is stored separately on different servers, making it highly challenging for the unauthorized users to reconstruct the original data. To further strengthen this approach, redundancy and distribution are employed, where data are spread across geographically diverse locations. This not only reduces the risk of localized attacks but also mitigates the impact of potential hardware failures. By implementing this method, organizations can minimize the risk of single point failure and increase overall security. Even if one server is compromised, only a fragment of encrypted data is exposed, which is useless without the other data. Additionally, this technique aids in compiling with data protection regulations by ensuring sensitive information is adequately safeguarded across distributed environments. Proposed framework. The proposed framework integrates homomorphic encryption and undercover sharing techniques to establish a secure cloud computing environment. This framework is designed to protect sensitive data while supporting efficient computation and strict access control. This process begins with the data encryption, where homomorphic encryption is applied to secure data before it is processed or shared in the cloud. This ensures that the data remains confidential even during computation. Following encryption, undercover sharing techniques are employed to divide and distribute the encrypted data across multiple servers, enhancing security by preventing any single entity from accessing the entire dataset. In addition, access control mechanisms are implemented to ensure that only authorized users can interact with the data. This layer of protection incorporates authentication and authorization protocols to safeguard the sensitivity information and restrict the unauthorized access. Data distribution strategy. Distributing the data across multiple servers plays a crucial role in enhancing security and data integrity. By splitting sensitive data and sharing it in various locations, the risk of unauthorized access is significantly reduced as no single server holds the complete dataset. This approach complicates the potential attacks, requiring advertisers to breach multiple servers to gain access to the full data. Furthermore, distributing data across these different servers improves data integrity, as even if one server is compromised or experience data corruption, the other servers maintain intact shares of the data. Another key benefit of this method is mitigating single points of failure. With data spread across multiple servers, the system remains operational even if one of the server fails or is attacked, ensuring continuity and minimizing disruption. This built-in redundancy increases availability and ensures that the user can still access services even if a server goes down. Additionally, it provides fault tolerance, allowing the system to function correctly despite hardware failure. In the event of a disaster, the distributed nature of the data allows for quicker recovery and restoration of services, making it robust approach for both security and reliability. Access control mechanisms. Implementing strong access control mechanism is essential for protecting sensitive data and ensuring only authorized users can view or manipulate inner information. Restricting access is crucial to prevent unauthorized access, reducing the risk of data breaches, and compile with the data protection regulations. By maintaining strict access controls, organizations can foster trust users and stakeholders, reassuring that the data is secure and handled responsibly. In proposed framework, among various access control measures are employed, such as role-based access control, which assigns users roles based on their responsibilities, granting them access only to the data they need. Additionally, multi-factor authentication adds an extra layer of security by requiring users to provide multiple forms of verification before accessing the system. The framework also includes audit trails to log accesses, attempts, and data modification, ensuring that all actions are tracked for monitoring and accountability purposes. Authentication mechanism plays a vital role in maintaining data privacy by offering granular control, allowing users access only to the specific data necessary for their roles. Furthermore, dynamic access management enables real-time adjustments to access rights based on user behavior or changes in roles, enhancing the security and adaptability of the system. Performance evaluation. To evaluate the proposed framework, performance tests were conducted with the goal of assessing its effectiveness and efficiency in securing the cloud data throughout homomorphic encryption and undercover sharing techniques. The test environment involved a setup that included multiple servers and standard hardware specifications along with the relevant software. Several key metrics were evaluated during the test. Encryption or decryption time was measured to gauge the speed of the data encrypted and decryption, offering insights into the efficiency of the proposed method. Processing overhead was another critical metric as it is access the additional computational resources required by the framework, helping to understand the impact of the overall system performance. Computational efficiency was analyzed under various loads of evaluated responses times and throughput rates. When compared to traditional encryption methods, the framework's performance was benchmarked to be highlighted improvements or possible drawbacks. The key findings of this performance evaluation offered insights into the system's speed, resource usage, and efficiency. Results, findings, and practical implications. The performance evaluation revealed several key findings in terms of encryption and decryption efficiency. The proposed framework showed a notable improvement over traditional methods, significantly reducing the time required for these operations and enhancing user experience. Regarding processing overhead, although there was a slight increase, it remained within the acceptable limits, ensuring the system stayed responsive. The framework maintained strong computational efficiency even under heavy workloads, demonstrating its scalability for real world applications. Overall, the balance between security and computational efficiency was well achieved. The dual approach of homomorphic encryption and data distribution proved the efficiency to protect and sensitive data without a major compromise in performance. while some trade-offs, such as increased resource computation, were identified, the security benefits overweighted these minor drawbacks. The proposed framework has broad applications in real-world scenarios, practically for securing data in cloud services and enabling safe data sharing among stakeholders. It is especially beneficial in industries like finance, healthcare, and government sectors where protecting sensitive information is crucial. Future work and conclusion. Future research and development in cloud security could focus on scalability enhancements to handle larger datasets and more complex operations, as well as real time processing techniques to maintain security while enabling immediate data access. Potential improvements to the proposed methods include optimization algorithms to reduce encryption and decryption times and improve system efficiency, along with user experience enhancements to minimize latency during secure data access. Further exploitation of additional security techniques, such as integrating multi factor authentication and blockchain technology for secure data sharing and integrity verification, could provide even greater protection. As cloud computing becomes essential for businesses, enhancing security is critical to safeguard sensitive data from evolving threats. The proposed framework, combining homomorphic encryption and undercover sharing, contributes an innovative solution that balances security and computational efficiency with practical applications across industries. Researchers are encouraged to build on these findings, while organizations should adopt advanced security practices to protect their cloud environments and sensitive information. Thank you.